Hello everyone, my name is Florent Koechlin and I'm currently a PhD student under the supervision of Arnaud Carayol and Cyril Nicaud at ICALP-B. I will talk today about Weakly-unambiguous Parikh automata and their link with Holonomic series. This is a joint work with Alin Bostan from INRIA Saclay, Arnaud Carayol and Cyril Nicaud. The link between formal languages and combinatorics is well known. It is established by considering the generating series of a language. Informally, this series counts the number of words of each length in the language, and more precisely, it is the infinite sum over all length n of ln x to the power of n, where ln denotes the number of words of length n in the language L. Below I give two classical examples of generating series. In particular, for the language of all words over a two-letter alphabet AB, there are 2 to the n words of length n. An alternative way to see this infinite sum is as the formal inverse of the polynomial 1 minus 2x. For well-known families of languages, such as regular languages and unambiguous context-free grammars, we have unambiguous descriptions of the language. Under the form of a deterministic finite automaton for regular languages, or an unambiguous context-free grammar for context-free languages. A grammar is unambiguous if every word is produced in at most one way. From these unambiguous descriptions, we can derive system of equations satisfied by the series of the language. For a finite automaton, there is one series per state, and for grammar there is one per non-terminal. For regular languages, the system is linear and its solution is a rational series, that is to say the ratio of two polynomials. For unambiguous context-free languages, the system is polynomial, and by solving it, we obtain a polynomial containing the series, which is the definition of an algebraic series. To sum up, regular languages have rational series, and unambiguous context-free languages have algebraic series, which is the Chomsky-Schustenberger theorem. Note that unambiguous descriptions here are crucial for the link to hold. If we consider inherently ambiguous context-free languages, we have no guarantees on its series. I am now going to present two applications of this link in automata theory. Our first example of application of this link is to show inherent ambiguity of some context-free languages. This means proving that no unambiguous grammar can describe a given context-free language. In the 70s, these questions were solved using tedious pumping arguments. The approach via counting, proposed by Flageolet, is to show that the series of the language is not algebraic to establish that this language cannot be described by any unambiguous context-free grammar. As an example, consider the product of palindromes, depicted here, which is a language of words that can be written as a concatenation of two palindromes. The proof via counting goes as follows. First, compute the generating series of the language, which was done by Kemp in 80. And then prove that it is not algebraic using analytic tools. For this example, Flageolet showed that the series has infinitely many singularities and hence cannot be algebraic. When it applies, this technique provides a quite elegant and powerful alternative to pumping techniques. Our second example of application is the inclusion problem for an ambiguous finite automata. An unambiguous finite automaton is a non-deterministic automaton in which each word is accepted by at most one run. For the inclusion problem, we are given two such automata, A and B, and we want to decide whether the language accepted by A is included in the language accepted by B. A naive approach would be to consider the intersection of B with the complement of A, which leads to an exponential algorithm because of the need for determinization when taking the complement. The counting approach allows to reason about the complement of A without the exponential blow. First, consider the case when L of A is strictly included in L of B. We give a linear bound on the left of a word witnessing this strict inclusion. We consider the series C, counting the words accepted by B and not by A. This series is simply the difference of the two series and is therefore rational. Furthermore, it can easily be shown that the degrees of the polynomial describing C are at most the sum of the number of states of A and B. Another classical result on rational series tells us that the coefficients of C satisfy a linear recurrence with constant coefficients of order R, where R is less than the sum of the number of states in A and B. Because we assume that the language accepted by A is strictly included in the language of B, the series C is non-null. Hence, one of its first or coefficients must be non-zero, otherwise by the recurrence relation, all the coefficients would be null. Stearns and Hunt gave a polynomial algorithm for the inclusion problem using this bound and the closure of an unambiguous automata under intersection. So here is the big picture we have presented so far. On one side, a hierarchy of classes of automata models, and on the other side, a hierarchy of classes of generating series. Holonomic series generalize rational and algebraic series and have been extensively studied in combinatorics. In this paper, our goal was to find a class of languages that complete the picture on the left with a natural unambiguous description and investigate the consequences of holonomicity for these automata models. Before presenting our results, I need to briefly present holonomic series. What is a holonomic series? Let me introduce it in one variable. A series f of x of the form sum of an x to the power of n is holonomic or definite if it satisfies a linear differential equation with polynomial coefficients. Here, the derivative must be understood as a generalization to series of the derivation of polynomials. Equivalently, a series is holonomic if its coefficients an satisfy a linear recurrence with polynomial coefficients. For instance, the exponential series, which is the formal series sum, the infinite sum of xn divided by factorial n, it is a holonomic series satisfying the differential equation f prime minus f equals 0, and it is not an algebraic series. This means that the class of holonomic series is wider than the class of algebraic series. For the technical parts of this talk, we need to introduce holonomic series in several variables. So a series in several variables is, just like in the univariate case, a generalization of polynomials with infinite number of monoms. A series in several variables is holonomic if it satisfies a system of linear partial derivative equations of this form. Notice that each line only depends on one variable. However, the polynomial coefficients in front are multivariate. Here, I recall that the partial derivative of a holonomic series is just the generalization of partial derivation for polynomials. However, for this talk, we don't need to understand fully this definition because we will mainly rely on closure properties of holonomic series rather than going back to the definition. Holonomic series in several variables enjoy a lot of closure properties. Here we put the main properties that we will need throughout this talk. They are closed under arithmetic operations, specialization to 1, which is replacing some variables by 1 and obtaining a new series with less variables, and finally under Hadamard's product, which is a component-wise product. Now that the extension on the right has been introduced, let us talk about the extension on the automata side. Previous attempts at a link between holonomic series and formal languages have already been done. Lipschitz explains, at the end of his proof of closure of holonomic series under Hadamard product, that it makes it possible to add seminar constraints to the number of occurrences of each variable on the monom of a holonomic series and still keep holonomicity. In 1993, Masatsa developed a ad hoc family of unambiguous context-free languages with linear constraints and proved using Hadamard product that their generating series are holonomic. More recently, Castiglione and Masatsa developed another class of language called RCM, which is a regular language with seminar constraints and an injective morphism to add expressivity. All these attempts are formal and do not relate to any used classes of unambiguous automata, even if Castiglione and Masatsa conjecture the link between their class and reversal bounding counter machines. The class of automata we propose to extend the hierarchy on the left is the class of Weakly-unambiguous pushdown Parikh automata. In this talk, however, we will forget the stack to emphasize the main ideas of the correspondence, so that we will only focus on Weakly-unambiguous Parikh automata. Parikh automata are a well-studied class of automata in model checking, introduced by Kladke and Ruth in 2003. They consist of a finite automaton whose transitions are labeled by a letter and a vector of a fixed dimension d, with non-negative integers, and a final seminar constraint. A run of the automaton is labeled by a couple word vector, where every letter is concatenated and every vector is summed. A run is accepting if it ends in a final state and if the vector sum of every vector seen in the transitions of the run belongs to the semilinear set C. Here we have depicting an automaton that expects to read at some point a full sequence of A's, then B's, then C's, such that the number of B's and C's is greater than twice the number of A's. In this example, the run depicted on the slide is accepting. It begins at an initial state, it ends in a final state, and the vector belongs to C. The word labeling the run is therefore accepted by the automaton. The accepting set C is not any set. As I said, it is what is called the semilinear set in ND, which is a Boolean combination of linear inequalities or equalities modulo constants. Semilinear sets are widely used in formal languages. They have several equivalent definitions presented here, and maybe the last one is the most important one for us. Semilinear sets are the unambiguous rational subset of the monoid ND. Why is it important for us? It is because this gives us information on the generating series. To any semilinear set, we can associate what is called its support series, an infinite sum of monomials, where we add in this sum the monomial x1 v1 x dvd, if and only if the vector v1 vd belongs to C. The fact that semilinear sets are an ambiguous rational subset of ND immediately implies that the support series are rational. For the link between automata and generating series to hold, we need a notion of an ambiguity. The notion of an ambiguity we consider is a standard one. For every word, there is at most one accepting run. We call such automata weakly-unambiguous because the name unambiguous Parikh automata already appears in the literature to denote another class. So, to avoid confusions, we adopted a different name. But let me stress that our notion of an ambiguity is the standard one. Here's an example of such an automaton, recognizing the language of words having an A in the middle. The semilinear constraint forces any accepting run to take the middle transition right in the middle of the word, so that every accepted word can only have one accepting run. As I said before, our class should not be confused with the class introduced by Cadillac, Finkel and Mackenzie under the name unambiguous constraint automata. For this class, the notion of unambiguity is much more restrictive than ours. They ask for the underlying automaton, without vectors, to be unambiguous. Our example here is a weakly-unambiguous Parikh automaton, but it is not an unambiguous Parikh automaton. Our first contribution was to relate this class of automata to existing classes. We showed that it corresponds to the class Theorem introduced by Castiglione and Masazza, and to the class of unambiguous reversal bound encoder machines introduced by Ibarra. From a technical point of view, this last equivalence is not surprising, as it holds in the non-deterministic case. However, it proves a stronger version of the conjecture of Castiglione and Masazza. In the presence of a stack, we obtain similar correspondences. However, from the technical point of view, the translations are much more involved. Now we have all the tools to prove that the generating series of a weakly-unambiguous Parikh automaton is holonomic. Let's forget about the semilinear constraints for one moment, and introduce the multivariate generating series of the runs of the automaton, where we count the runs of the automaton from an initial state to a final state, sorted by length n and by their labeling vector v1, vd. This generating series is rational by a direct translation from the automaton. As we already said, the support series of the semilinear set is also rational. The generating series of the accepting runs of the automaton is expressed by removing from the series the runs labeled by a vector that does not belong to the semilinear set C. This is done thanks to the Hadamard product. As the Hadamard product of two rational series is holonomic, the resulting series is holonomic too. Finally, we specialize the variables concerning the vectors to 1, preserving holomicity, to only keep a series counting the accepting runs by length. As the automaton is weakly-unambiguous, counting the accepting runs of length n is equivalent to counting the accepted words of length n, so the generating series of the language recognized by the automaton is holonomic. The first consequence of this result is a criterion to prove inherent weak ambiguity of Parikh automata languages. exactly in the same fashion as the technique of flageolet for ambiguous context-free languages. Let us give an example of such a technique. The language D, which consists of blocks of A separated by B's, such that at some point in the word, one block is not inside the double of its preceding one. A typical word not in D is the word AB, A square B, A 4 times B, A times B, where each block is the double of its previous one. These words not belonging to D make it possible to easily compute the generating series of the language. It has infinitely many singularities, which is incompatible with holomicity. Hence, D is inherently weakly ambiguous for Parikh automata. However, this method is not universal. It is only a sufficient condition. In fact, inherent weak unambiguity is undecidable. This follows from a general theorem of undecidability of Greibar using the undecidability of universality for general Parikh automata. It turns out that inherent weakly ambiguous languages can have very simple series. In the paper, we give an example of an inherently weakly ambiguous language whose series is rational. This language, called L11, consists of sequences of pairs of blocks of A's separated by a B, such that at some point the two blocks in a pair have the same size. The generating series of L11 is rational, but we showed using a quite involved pumping techniques that this language is inherently weakly ambiguous. In fact, our proof shows that this language is inherently ambiguous even if the Parikh automaton allows any recursive constraint set instead of just a sublinear set. The second consequence is of algorithmic nature. The problem we consider is the inclusion problem for weakly unambiguous Parikh automata. We are given two weakly unambiguous Parikh automata, A and B, and we want to decide whether the language of A is included in the language of B. This problem has already been studied in some cases. If the automata are deterministic, the problem is co-NX complete, provided that the sublinear set is represented by an existential Presburger formula. In the weakly unambiguous case, the decidability of the problem can be derived from the work of Castiglione and Masazza on RCM using our equivalence result. However, their approach does not provide any upper bound. For non-deterministic Parikh automata, the problem is undecidable since the universality is already undecidable. Our goal here is to derive an upper bound on the inclusion problem for weakly unambiguous Parikh automata using the counting approach. We are going to proceed similarly as for unambiguous finite automata. We are first going to bound the size of a witness for non-inclusions in terms of the size of the automata, and using these bounds and the closure of weakly unambiguous Parikh automata under intersection, we will derive an algorithm. We assume that the language accepted by A is strictly included in the language accepted by B, and we want to derive a bound for the length of a word that is in B and not in A. For that, we consider the series C, which counts the number of words that are in B and not in A. This is exactly what we did for unambiguous finite automata. In this case, we saw that C is rational. We had a linear recurrence equation satisfied by the coefficients, and if you recall, the key point was that we could bound the degree of the series A by the number of states of A. Same thing happened for B, so that we could compute the degree of the difference of the two series, which is almost the sum of the degree of the two series. From that, we could obtain a bound for the order of the recurrence, and from there, we could finally bound the length of the smallest witness of strict inclusion. For weakly unambiguous Parikh automata, the situation is a bit more complex, because C of x will no longer be rational. It will be holonomic, and the coefficient will satisfy a linear recurrence, but with polynomial coefficients. Here, there is a key difference. It is no longer enough to know the order of the recurrence to derive our bound. For instance, if we look at the polynomial below, it is not equal to 0, but it satisfies the differential equation of order 1 and the polynomial equation of order 0. Clearly, the first terms of the coefficients are 0, whereas it is not 0. This comes from the fact that the leading polynomial of the recurrence relation has a root at 100. So for n equals to 100, the equation is simply 0 equals 0. so we have no information for the value of the series at this point. This means that we have to check that up to this point, all the coefficients are 0 to ensure it is always 0. And this is not the case for c equal x to the power 100. In general, if the series c is not 0, it will contain a non-null coefficient before the sum of the order of the recurrence and the largest integer root of the leading polynomial. Let's come back to our proof. We need to compute the size of the representation of a and b in terms of the size of the automata a and b. By size of the representation of a series, we mean not only the order of the equation, but also the size of all the coefficients, which, remember, are polynomials. From there, we can compute similar bounds for the difference of the two series, then finally for the order and the largest root of the leading polynomial of the recurrence. These last two steps are quite simple, and our key contribution was in establishing the bounds for the series of a weakly-unambiguous Parikh automaton. Remember that the generating series of an unambiguous Parikh automaton is obtained as a Hadamard product of two rational series, one obtained from the runs of the automaton, the other one from the seminar constraints. These generating series are easy to compute from the automata describing them. The main difficulty is to provide bounds for the Hadamard product of them, and we do this by a detailed analysis of the algorithm of Lipschitz that proves that holonomic series are closed under Hadamard product. After doing all this analysis, we obtain this following bound for the smallest witness of strict inclusion. Of course, we need to fix a representation for the seminar, and in this paper we assumed that the seminar was given under an unambiguous representation, and that the vectors of the Parikh automata were coded in unary. With these restrictions, the bound is doubly exponential in the dimension d, and if we fix the dimensions of the Parikh automaton, it is simply exponential in the size of the automata. From this proposition, using dynamic programming to compute the number of accepting words, we can derive a 2x timed algorithm to decide inclusion for weakly-unambiguous Parikh automata. To conclude, I recall here the fully completed picture we have studied so far. Remember that the real class extending the hierarchy for automata models are Parikh automata with a stack, to include, for instance, context-free languages. There is still work to do to have a better understanding of this picture, as some questions remain open. Some closure properties for automata are still open, like the closure of weakly-unambiguous Parikh automata under union or complement. We also haven't studied yet the exact theoretic complexity of inclusion for weakly-unambiguous Parikh automata. The inclusion problem cannot be solved like we did when we'd add a stack, because pushdown Parikh automata are not closed anymore under intersection. But another interesting algorithmic problem that we could look at is the question of universality of weakly-unambiguous pushdown Parikh automata. Another perspective would be to find better upper bounds for inclusion, either by involved automata techniques or by better algorithms to handle the Hadamard product. Finally, another interesting question would be to try to extend the class of languages we studied by adding non-seminar constraints, while still keeping a holonomic series, so that we could use our techniques to a wider class of languages. However, this is not possible since Bell and Chen proved that the support series of a set is holonomic if and only if it is the support series of a seminar set. So as a consequence, we need some new ideas to obtain some languages that have holonomic series. Thank you for your attention.